Brian Plowski, DriveScale. I'm here to talk about our integration of composable infrastructure with Kubernetes. Like this entire track has been about Kubernetes. Hold on, everybody smile. Hold on here, and I'll just do two pictures. That's it, yep. Need to show marketing this. Anyway. So, what I want you to think about when you're listening to this talk, I'm going to talk about kind of juggle three balls in the air, but the thing that is important here is, this is a summary slide. DriveScale Composable Infrastructure Platform, which I'll describe, it seamlessly integrates with Kubernetes to provide, the important part is performant dynamic volumes that allow you, this is almost marketing, data-intensive scale applications under this emerging data center orchestration without compromise. And the three things are, we do composable infrastructure. We had a lot of focus on scale-out applications and providing a way to separate compute and storage out without compromising those applications' performance requirements. And how does this all frappe with the emergence of Kubernetes as an orchestration for scale-out deployments within the data center? Okay? I'll try to touch on all of this. Talk about Kubernetes. I'm going to go pretty fast through Kubernetes container storage interface. There was a great talk earlier today from the Docker person, first session after lunch, about the CSI interface. That was very well done. A little bit about scale-out applications. You know what they are. I'm just going to touch on a couple of things to keep in mind while I'm talking about our solution, and then talk about very quickly what composable infrastructure is from the DriveScale position. There's a lot of people that are saying composable infrastructure, and you'll hear lots of talks, and just take my definition for it now, and I'm not worried about the other people. DriveScale CSI plugin for Kubernetes. Bring all three things together and talk about some of the future stuff. The previous talk on LinStore was touching on some common problems that people are running into. So the emergence of persistent volumes, persistent data solutions to Kubernetes, which kind of arose out of containers and dynamic ephemeral application deployments, that with the addition of persistent volumes and persistent data, we're kind of wrestling with some stuff. He was talking about locality, basically maintaining the location of data closer to the application to continue its performance. So that talk was good too. You should probably go, if you didn't see that talk, go back and grab the slides and listen to the audio. So, technology trends. Three things, it's interesting. There's probably many other things that have happened in the past 15 years. However, three things I thought were kind of fascinating to be coexisting. So, virtualization is not new. I tried to tell the VMware guys this years ago, but what was new was commodity virtualization and the extent to which it was deployed. And somewhere around 2006, 2007, I think I was in Cambridge when AMD and Intel announced they were adding hardware support for virtualization as they tried to figure out what to do next. And as virtualization took over, it changed a lot of the way people thought about applications in the data center. Initially, it was to save, in a similar fashion, it's this related to containers, in that it's meant to be an efficiency play to allow you to load balance, deploy applications, and not worry about the details of how you're pulling that off. Virtualization was a completely transparent solution to the application deployment. You know, basically, VMware made the operating system the application library. You made a VM image and you moved that around. It was nothing but a library after that. A very heavyweight library, by the way. But something happened around virtualization that I think people noticed after they were deploying it to solve a performance utilization efficiency problem, was that software management of applications became a very powerful tool in the data center to get control over the sprawl and was much better than the former method of I will deploy a physical hardware server and then install my application. One button push applications took over the world. So anyway, roughly around the same time this was happening, completely independent, the hyperscalers were basically making scale-out applications the norm for handling huge amounts of users, traffics, and data analysis. So the classic poster child of this is, everybody say it, Hadoop, okay? The hilarious part in about 2010 was a guy walks into his IT guy in a data center and says, I need 500 nodes to deploy this application Hadoop. And the IT guy goes, what's Hadoop? He goes, not important now. I just need to run it because it's going to make us save money and monetize things you could never imagine through data analytics. And the IT guy goes, well, I'll give you 500 virtual machines. No. I want 500 bare metal machines to run this application you never heard of. That was a lovely part of the scale-out applications. They were designed in a way that had nothing to do with virtualization. The virtualization trend solved something completely different. I have to hurry up. Scale-out applications, bare metal. Containers. Let's go forward. They emerged as a response to some of the problems, a lot of the problems, in virtualization, in the classic sense. So, as I mentioned, came from scale up. You want to deploy an application, provision hardware. Virtualization, you want to deploy an application, deploy a virtual machine, operating system and all. Beauty of this was Windows applications, Linux applications, blah applications, they could all run on a single machine. All interpreted by a hypervisor running on its own operating system. Virtualized deployments, brilliant. Containers. Run your apps with their libraries on a kind of sort of virtualized environment in, like, say, Linux, where they're just running the library specific to the app. They're coexisting, but they're protected in the similar fashion to virtualization without the heavyweight operations. Now, keep in mind that the claim of the virtualized platforms was you didn't have to change your application or your operating system. You just deployed it on top of the thing, right? Let's ignore para-virtualization for now. Containers are not that transparent, right? Containerization is a thing. So, containers. Operating system level virtualization, multiple isolated systems, single physical host. Lightweight, megabytes for containers compared to gigabytes for VMs. Only one real copy of the host system, yeah. Anybody have anything to say back there? God. Anyway, common libraries can be shared, but they are lighter weight, right? One of the things, I didn't put it here. One of the things that having to do with the fact that you're not dragging around an operating system with you is to start your application. You don't have to boot an operating system every single time you spawn an application. So it comes up faster, it's smaller. Less load on the system. Less I/O virtualization, so higher performance for containers, possibly, than having to go through the translation layers of the virtual machine. Containers are hardware agnostic and platform agnostic. They're just not operating system agnostic. They can run on your laptop or bare metal. Everybody loves them. And containers can simplify scale-out application deployment because here's going back to that slide before. The scale-out application people did not specify it in terms of virtual machines. It just really didn't work from a performance standpoint, and it gave nothing from a deployment standpoint, given how the applications themselves were being designed. However, containers with lightweight model can give you one of the benefits that came with virtualization. Software control and orchestration of your applications being deployed in your data center at scale. Okay? Can. Okay? But does it? So when containers came about, by the way, I mean, that first slide, the previous slide, that was containers without Kubernetes, right? So containers by themselves are a packaging exercise. Scale-out applications are, say, 1,000 nodes just to get friendly out there, right, and do something useful. Containers at 1,000 nodes require something else. Kubernetes. I'm not even going to waste the few remaining years of my life to talk about the other orchestration systems. Okay? So, Kubernetes, open source container orchestration platform, you know this. Started at Google, now at the Cloud Native Computing Foundation. It has gained a lot of traction and momentum very quickly. A colleague of mine, Blake Lewis, said after I said it means helmsman, which everybody knows, to also remind you that it's the root of cybernetics. Essentially, Kubernetes manages clusters of containers on multiple nodes. Containers by themselves do not have any point with scale-out applications. Orchestrate them at scale, then they become interesting. Okay. Any questions, objections, anything like that? I've thrown various technologies under the bus. All right, CSI. I'm not even going to talk about the predecessors of CSI. A method of adding external storage providers to containers has been defined, called CSI. There were other variants before this, but CSI is taking, it's getting all the attention. It is not Kubernetes specific. It does work with Meso and Docker Swarm, I believe, and Docker Swarm is going towards this in probably over their native method of doing storage for containers. So, if you were me, if I were you, I would not worry anything except CSI moving forward, by the way. So, preferred storage provider moving forward for Kubernetes essentially allows third-party storage providers of any kind to plug in to Kubernetes without being in tree in Kubernetes. So you can basically operate on your own time frame and integrate when you can, when you want to. It is about persistent storage. I mean, they're doing some stuff with ephemeral storage, but not really important now. Supports dynamic provisioning and deprovisioning of a volume. The applications, when you launch pods themselves, can request generic storage of a certain type, and then the storage providers can create that storage, allocate it, and provide it to the containers for use. So it can be all very dynamic. So the thing about CSI and a couple of recent predecessors, this is all very new. So CSI became stable, I think, in 2018 with, I want to say 113, right? Is that it? Yeah. Kubernetes 113. That came up in one of the other presentations. So before things like CSI came along to support persistent data, persistent storage, a lot of the container work was being done with microservices that were essentially using local storage being spun up and spun out, but not focused on these applications that DriveScale is very much interested in, which is the scale-out applications that are doing a lot of crunching on persistent data. So data analytics applications, scale-out databases, all of your favorites, Cassandra, Sola, Aerospike. All of these are persistent data applications, and they need a way to be used and deployed over in containers with Kubernetes. You do really want a way to kind of do this cleanly in a standard way, and that is CSI. I talked about scale-out applications. Let me see if there's anything I missed here. Virtualized, I mentioned all that. I mean, virtualization, in the end, its lasting impact was as a first real standard for software orchestration of application deployment. Scale-out applications, again, commodity platforms. One thing in it, because I'm going to transition to DriveScale, was that they were specified in terms of compute and storage co-located. Bring the application to the storage, optimize. The application owns its own storage stack. Each storage stack is different. It's all application specific. Availability and recovery are all application specific, application defined. They run on bare metal. If you do things like introduce VMs, you just introduce performance problems. You're basically funneling through virtualized interface the I/O that essentially wanted to go directly to the storage that the applications are optimized for. Things like NAS basically introduce bottlenecks by funneling lovely distributed compute and storage I/O into funnel points that essentially created additional performance problems. SAN, of the traditional fiber channel sense, didn't scale to anywhere near the scale that they wanted to use with standard Ethernet, commodity hardware running all over the place. So, scaled applications, scratch a scaled application, you're going to find triple replication. Recovery mechanism is rebuild. Regardless of usually what it's attached to in the end, you can put interesting storage in the back end, and the application is still probably going to do what it's going to do anyway. Performance achieved with local direct attached storage, either with spinning disk for a lot of the sequential workloads, and SSDs today, flash drives, flash storage, for the high performance random I/O database workloads. Here's the thing. Important thing to remember. The scale-out applications are the important part of this equation. The only thing that Kubernetes could possibly add, if anything, is actual manageability and orchestration at scale with a common framework for multiple scale-out applications. It doesn't actually change anything about the application itself. The application is the application. It still has its storage stack in it. A high-performance Aerospike database is designed to use the SSDs that it has access to in a high-performance way to generate millions and millions of transactions per second and only lose 5 or 6 at a time. But, and that's true. It's mostly, right? Kubernetes has to stay out of the way. This is why VMs don't work. VMs want to do more. Scaled applications don't want you to do anything at all. They essentially want direct attached storage to their nodes and as many nodes as they want to give you the performance and facilities that you need for your business. So Kubernetes can add value to all this by doing something useful, by orchestrating at scale in a common platform. And because of the addition recently, this is all moving very fast. I have a timeline at the back of my slide you can amuse yourself with. I think the Docker guy doing the CSI talk had a much more interesting and complete timeline, but it's all kind of new. Persistent volumes and settling down on a standard around it is the enabling piece to use Kubernetes with scale-out applications, in my mind. Yeah, DriveScale. So, scale-out applications, very quick, forget this. Scale-out applications defined in terms of commodities off-the-shelf compute with embedded storage. End of story. I mean, you can tell me other people provide solutions for it. Show me all those deployments. And I know the cloud is there, but this talk is not about the cloud right now. So here's the thing. Each application has different requirements of compute to storage that is fixed when you deploy the node and then you horizontally scale. And you can mix nodes up as generations change. But you do have to have storage within a node. I would observe that for something like Aerospike with 24 SSDs in a compute node for the database application, that the node that Aerospike deploys off the shelf with 24 SSDs is what the enterprise storage vendors ship as their storage product for their low volume business. Here's the thing. You're stretching the definition of a commodity off the shelf part if you're buying the lowest volume product from Dell because you are defining a compute blade that is the same as everything else in their line with a lot of disks in it. So And it varies from machine to machine. Some are running disks, some are running SSDs, mostly NVMe these days. Some want 4, some want 8, some want 12. These are all special numbers. These are the configurations you can buy from Dell. Or some want 24 drives. If you don't want 24, but you need 13, you're going to buy a 24-slot machine and pay the empty slot cost for blowing air through a bunch of space in your data center. Okay, enter Composable Infrastructure. This is the solution to every problem you have in your data center today. So Composable Infrastructure says, take your nodes with captured storage, go with lightweight blades, pull the storage out, and access it over high-performance fabric, and match compute and storage, disks, SSDs, whatever's needed for your application SKUs, and mix and match. So reduce your SKUs, use compute nodes that are optimized and cheap, and then aggregate storage, disks, spinning disks, and flash, and divide them up and access them as if they have extension cords on them to your compute nodes. So it's software-defined infrastructure. You're basically making your servers on the fly when you need them. Just saying the same thing. So, I mean, these things all happened, well, iSCSI's been around forever, but the NVMe movements, NVMe fabric have really been enabling and taking off a lot of the performance objections to finally just laying this all out on the network. There's some performance data on the Aerospike site. That's a fairly high performance application where we posted our results comparing fabric accessed SSDs versus local SSDs for the Aerospike certification test suite. Lower cost, smaller footprint. Decoupling, there is one thing that the enterprise storage vendors got right, by the way. The big argument from total cost of ownership of enterprise storage is pay us a lot of money for our storage because we separate out compute from the storage. You can manage the life cycles differently. Don't couple the life cycle refreshes with embedded storage within the compute node itself and manage it, do multi-vendor, get your cost down. So in one sense, disaggregation, composable infrastructure for things like scaled applications where we're doing this DAS model on the network is returning back to a separating compute and storage out, but without any of the, we vend whole disks essentially. You'll see more about that in a second. How am I doing? Okay. So, let's go talk a little about DriveScale and Kubernetes. From a DriveScale perspective, we essentially take disaggregated compute, thin compute blades, storage, vended through Ethernet attached JBODs, JBOFs, with some compute to present them as whole disks or whole SSDs mostly. And we compose them within the data center to be in dynamic clusters and dynamic platforms for scale-out applications. So in the DriveScale world, there's application clusters. You don't put your Hadoop cluster in the same compute nodes as your ScyllaDB. You just don't do things like that. They're all separate, dedicated clusters. We're just allowing you to dynamically compose them. So each cluster within a data center is running its own application. And then you'll have some inventory for replacing failed disks or a failed server. Again, going back to the virtualization model, composable infrastructure is trying to go into a software-defined infrastructure model, except we're doing more hardware management. And I'll get to that in a second more. From the Kubernetes perspective, working with DriveScale, Kubernetes clusters would overlay clusters in the DriveScale management domain. Kubernetes is the software overlay doing the application deployment and management. We don't deploy applications, we just provide the physical infrastructure. So each Kubernetes cluster would correspond one-to-one with a DriveScale cluster. Of course, within DriveScale, you can have clusters unrelated to Kubernetes. We operate at a data center level when we're doing our orchestration. You get a little bit to my concern or confusion around what do you call it? Kubernetes. There's this thing here I want to talk about in a little bit, podwatcher. Pod being the unit of management for Kubernetes. It basically bundles the containers into something that's scheduled and moved around. So I don't know where this is going to end up eventually, but our impression at DriveScale is that essentially Kubernetes clusters are being deployed with a master and a cluster, one-to-one. You don't manage multiple clusters today, really, with multiple Kubernetes clusters with a single master. You're not much doing that. We're pretty focused on scaled applications. So the way our customers are thinking about this is they're going to deploy a Kubernetes cluster for one application, a Kubernetes cluster for another. But from our viewpoint, we manage the hardware globally, data center wide. So doesn't mean somebody couldn't run multiple instances of our hardware manager, but I don't know why they would do that. So from our perspective, the clusters overlap into our DriveScale cluster of physical management. We have a composer, an engine that basically orchestrates the hardware. Kubernetes orchestrates the software on top of the compute nodes. And there's a little squint your eye thing in here, yeah. So Kubernetes clusters maps into a single DriveScale cluster. Each of those DriveScale clusters exists within a DriveScale domain. Squint your eyes, I want you to believe that Kubernetes is the software orchestrator. Kubernetes is not really good at the hardware management level of things. And that's where DriveScale thinks we have an opportunity to add some value to this whole problem. DriveScale is absolutely the hardware physical orchestrator. We essentially allow you to, just in time define a node for use with your scale out application. The only thing that we need for Kubernetes nodes, pretty much, to interact with DriveScale is to run the DriveScale server agent on the compute nodes, what's called nodes in Kubernetes. Multiple Kubernetes clusters, I mentioned this, will run in the DriveScale domain. DriveScale clusters are created dynamically from Kubernetes. I can touch on it a little bit. Kubernetes clusters can exist outside of it. I think I covered this. By the way, when I was kind of going through this talk, Kubernetes uses etcd for essentially doing desired state achievement for when you're doing configuration changes. It's sort of essentially when you do something, orchestration at scale out, you have to have a way of doing availability, durability of the configuration management and changes you really can't forget. And you have to be consistent. You can't allocate a node to two different people. You can't forget where you are. So the configuration changes have to be durable and consistent. In the face of controller, node failures, and network partitions. So here's the thing at scale. Once you start spreading yourself out, then these issues become very important. And it turns out that Kubernetes and DriveScale are taking a similar approach. Kubernetes is using etcd, DriveScale is using Zookeeper, which has a concept of moving from moving from a consistent state to a consistent state and having a desired state being an outcome of a configuration change. And all of the components participate to achieve that desired state. So what I'm trying to say with this line here is DriveScale is taking a similar approach, so we feel like we are not going to screw anything up in your Kubernetes deployment, if you believe in the Kubernetes approach. The only things you really need to know that Kubernetes gets configured as part of the CSI DriveScale driver when it's installed is you need login information to our DriveScale manager, the server address, it's a highly available server, and then the cluster name that will match the Kubernetes cluster, which is probably the same name as a Kubernetes cluster. But you have to push that in. That's really all that's needed. And then for each storage provider, you have to create a storage class that is the dynamic allocation method for your pods, and our provisioner name is csi.drivescale.com. So this is all standard CSI stuff. Let's get down here. So the CSI driver supporting persistent volumes is symmetrical, create, publish it on controller, stage it on the node, and then publish it on the node. I'm going to talk a little bit about what that means. And then when you basically delete storage or move a pod and you want to detach the storage, you essentially reverse the steps. And this is all, I have a bunch of references at the end of the talk for the CSI documentation. It makes for an interesting read. So, some things that happen. So we are talking about persistent storage. And yeah, I'm doing that. We are talking about persistent storage. So a couple things that happen. You have a Kubernetes cluster. You've installed the server agents and you install the CSI driver. You have a DriveScale deployment with hardware. The application is deployed on Kubernetes and requests storage. So one of the first things it does is it creates the logical cluster within DriveScale. It doesn't exist beforehand. You don't have to pre-allocate the cluster. You have the agents installed from DriveScale on the nodes that will participate. But they don't actually do anything from our perspective until they start consuming storage. So we will create a logical cluster as a side effect of you creating the first persistent volume within the cluster for your pod deployment. And these are our DriveScale API calls that the CSI driver calls to us, adds a logical node, it's our management entity, adds drives to the logical node, maps drives to the logical node. That's a little thing we do. And then it then starts to attach the drives to the server. And that's a second step, and it is the controller publish volume step within Kubernetes CSI API. So the important thing here is that from the CSI perspective, to use the controller publish volume call allows you to attach and detach the persistent volume from the node, which allows you to move the pod without losing the volume. So you can skip, you've got to read the CSI documentation. I'm not going to go through it right now. But you can skip like kind of this part. But then you are linking the pod to the persistent volume in a way that doesn't allow you to move it. Okay? So this step is basically you want to be able to migrate pods easily. So you have to have them you have to have the persistent volumes kind of logical entities that are related to the pods but not tightly bound to them. That's how I view it. I want to go into this drive stuff. Conceptually, again, going back to drives, conceptually, a persistent volume maps to a single drive in the DriveScale world. Now, a pod can have multiple drives. That's possible, but there is an instance where it will create multiple drives on demand. And by the way, the next steps are the mount operation. It mounts the configured block device with a file system to the node, and then it binds the file system to the pod and container. Okay, drive types. So in the simplest case, when you create a persistent volume for DriveScale, it's classic DriveScale. You'll get one hard disk or one SSD. Again, we're not virtualizing storage. We don't do compression. We don't do much of anything really, because we don't want to. So if you want to do that stuff, you can buy any number of storage options and plug them in through the CSI driver, through the storage providers, provide a CSI driver, and blow your scale-out application performance out in the water. Because they want raw disks, right? The one thing we do is this SSD slicing. So we had some customers run into a couple of problems with SSDs. One, the SSDs capacities were growing, and they did not need that much SSDs for certain applications they were running. So they might need an SSD and some spinning disk, and the SSD is a log device within the node, and they want a small amount of log device. But when they do the math, they're finding out that an 11.86 terabyte SSD is a really good price performance point from how they view the world. Except it's not a good price performance point if you basically had embedded SSDs in compute nodes and you're only using 1 terabyte of 11.86 terabytes, because then you're just wasting space. So when you disaggregate, you start thinking differently about the economics when you are allowed to share them. So we introduced this thing called slicing. Basically, there's enough random IOPS for most of these applications where they're looking at this SSD slicing to essentially vend portions of the SSD to different clients and mount them as smaller devices. It's an application for us. Things like Aerospike, they want all the SSDs. They're not slicing. They just want lots of SSDs. But for certain applications, they want slices of SSD. So we do this SSD slice. But from the application perspective, it looks just like a drive. Okay? It just looks like a drive. So you can set an option in our CSI driver that says you want availability, redundancy. Again, there are certain applications who specify their deployment on bare metal to be on top of mirrored drives. It's not something we say. The application would be doing local RAID mirroring for a la Linux on top of raw disk. 2 drives in a mirror configuration. We support that automatically through the provisioner. If you say I need redundancy, then you will get RAID 1 mirroring. But through the Linux RAID system. We don't RAID on our end. Again, we're just like a thin layer. We're not in a data path. We just set things up using standard piping, plumbing things together. One thing we're doing for, one thing we're doing for the dynamic volume allocation is if you request something larger than anything you have in inventory from a full disk size, we will stripe whole disks for you to give you the volume of the persistent volume of the size you want. However, without telling you this, we will mirror it because no one should be striping a bunch of disks together just because your failure rates go up as you add drives. So we'll do RAID 10 mirroring and automatically allocate larger drives than you've asked for. Kind of neither here nor there, but we're trying to basically let the CSI driver dynamically provision stuff without you having to decide every single thing at scale, okay? But you can control the behaviors. How am I doing? I'm doing good, okay. I talked about SSD slicing already. Oh, obviously, by the way, so slicing is not enabled for spinning disk. The scale-out applications that are using spinning disks are doing sequential I/O. What's the best way to ruin someone's day that's optimized for sequential I/O? Put 2 applications on that disk, right? And you have now created a random I/O workload. So we don't slice spinning disks. It's only a SSD thing. Plus, spinning disks don't have the IOPS even on a good day. One thing we do, so this is something that we just changed in our CSI driver. We support data encryption over the wire and at rest, obviously because we're doing it over the wire that's stored at rest, of both the metadata and the data. We have a built-in key generation, key management system that automatically generates drive keys for your data. Because, again, DriveScale is all about selling into like scale-out applications what are the common use cases of scale-out applications? All of your personal data for doing ad determination and placement and stuff like that, which is now falling under the GDRP. GDRP, right? Right, GDRP. I always get those letters confused. So anyway, so we basically, for the Kubernetes plugin, our major customer is switching over to putting their scale-out application in Kubernetes. Again, this stuff is all new. They're going to be deploying Kubernetes. In the meantime, they have asked us, or observed to us, that they are going to enable encryption over everything at this point. They've sort of decided, instead of slicing and dicing the data up to what had to be encrypted and what didn't have to be encrypted, the easiest solution to all of this is just to encrypt everything. So our Kubernetes CSI plugin moving forward has encryption on by default. You can turn it off if you want, you know. I mean, this is the whole argument of, yeah, but encryption takes performance. I don't, you know, my performance is important right until your credit cards are splayed out across the internet. So, again, so here's the thing. What does DriveScale value add in here? All right. Transparent to your applications being deployed on Kubernetes. We are choosing automatically the highest performance transport over Ethernet between the compute and storage. If you have just iSCSI, we plumb iSCSI. Do you need to know anything about iSCSI? Not at all. It just connects. What's the point of you having to learn all this stuff? What were we doing? If you upgrade your Linux end-to-ends and enabled NVMe TCP as part of the upgrades on the clients and on your server controller, then you will get NVMe over TCP automatically, unless you explicitly say don't do that. And the same thing goes for Rocky. You know, so RDMA is being spec'd for certain applications, and if you basically install RDMA NICs in both ends and have the switches enabled correctly, then RDMA will pop up. But you don't have to do anything in our deployment. We will just auto-discover the capabilities end-to-end. The same thing with the encryption. You don't have to go read the book on how to enable encryption and then figure out, go get a package of distributed keys. You just say, please encrypt my data? Well, actually, you don't say anything now moving forward with the CSI driver. If you have to say, don't encrypt my data to do something, otherwise your data is encrypted. All right. Oh, there was a comment in the previous talk. Again, gonna watch my hands. Again, these applications are specified in terms of bare metal local DAS. That's just what people think about them and how they want to deploy them typically at scale. So one of the things that if the application wants compression, the application's doing compression. So their database is there. They're doing compression. They're not looking for compression on the back end. They're basically distributing the compression problem over all the nodes, scale out, because they don't know how many, if they wanted more compression, there's more nodes. It's a scale out application. Every application we're interested in is scale out. So the compression is out there. So, encryption. The application is doing the compression. Our encryption is not preventing compression from happening because it happens above the over-the-wire encryption that sits below the application. All right? Enterprise storage arrays at the other end of the problem, if somebody wants over-the-wire encryption, have a certain problem with doing compression. Deduplication at scale in a distributed sense is somewhat complicated. So most of these applications aren't pursuing deduplication. So you got to think about where we are in our wheelhouse. I mean, we run other applications if you want to, but we think of that as something, if you're using us to manage in the data center your physical assets, you're doing, here's multiple reminders. You're doing something different. Okay, don't need to go over this. This is essentially, all this is local disk formatting options. We're not a distributed file system. We're giving you a local disk with an extension cord on it, and you can set the methods for formatting and redundancy. You could control the transports through the CSI driver too. Again, this is something you could do within our composer, but so that's not important. There was that thing I mentioned in each Kubernetes cluster. We do launch a little helper agent called a podwatcher. So the thing about, this was mentioned in one of the talks earlier today. So Kubernetes is not telling us a lot underneath of what's going on. So when you pop open our Composer, our GUI system for seeing what the hell's going on, you'll see the Kubernetes clusters, but without a little help from podwatcher, you're going to see a lot of meaningless strings of very long UUIDs attached to a PV, with a PV prefix, which is the persistent volume. We basically, it's easier to show, basically a podwatcher in each Kubernetes cluster that watches the pods. And for pods that are being used with us, you can look at this offline, we are essentially connecting the pod, naming the pods that are in a given node by the name that they've been spun off with. So this is which one is this? MongoDB pod talking to a RAID 10 volume on a set of disks and what the disks are and the persistent volume identification. We're actually looking to kind of mine some more stuff out of Kubernetes to make that more human intelligible for debug purposes. Oops. I'm going to do this one. So, yeah. I just want to talk, can I talk, any questions that are burning right now? Yes. Oh, you were asking questions before you. Yes, what? No, you. You were sitting here. Yeah.
It's the same thing. So what about locality and all this stuff?
Yeah. Well, it sucks. So, as the previous talk was going over, not Kubernetes strength, right? I think it's a problem introduced by Kubernetes. So, Kubernetes wants to load balance and move pods all over the place, right? Without perhaps regard. It all made sense when all the storage was local to the container, right? What's the locality? It's all there. You move the container and everything's still local. It's fucking brilliant. So, persistent volume introduction meeting Kubernetes is a fertile ground for innovation. So our DriveScale solution has the capability of essentially auto painting the network topology between the storage and the compute nodes, and then deploying fault domains, preventing you from basically creating a RAID array with all of the disks, creating a triple not RAID array, so the applications are all triple replicas, putting all of the replicas in a single JBOD, that would be bad, right? Because the JBOD, you just destroyed the application. So we already have this logic. It's an important part of our product to essentially not have you worry about data placement, but basically insisting on fault domain, rack aware. Second thing is bandwidth domains. Making sure you're not giving somebody a disk that happens to involve several hops away from the compute node, because our goal is to be the same as local disk. So we're bandwidth aware and fault domain aware. And to Kubernetes. So we're not, we kind of know what's going to happen, but then if Kubernetes is moving pods around wildly because it's load balancing, right, that doesn't actually help us. So the biggest thing, the biggest thing right now is you have to kind of manually deal with this in Kubernetes, is my understanding. But we can recognize all the bandwidth and failure domain information. We're trying to figure out, moving forward, how to kind of push this up into Kubernetes and take advantage of probably things that are coming out in Kubernetes that address this problem. Again, yeah, this wasn't a problem when there was only container local storage, right? But persistent volumes is new. I mean, they've been around for a couple of years, and that's kind of new. And their deployments and the issues with them are still being worked out. But we think we already have this solved for bare metal deployments. We just need to kind of integrate it with Kubernetes moving forward. Does that help a little bit? I'm not trying to be wimpy here. Okay. A couple other things. Shoop. I skipped one. Oh, sorry. That's the important one, actually. I actually think the previous talk mentioned this too. So Kubernetes is somewhat I don't know, easygoing about hardware failures. How do I describe this? When your node fails, Kubernetes, this is the classic problem, right? Kubernetes doesn't know whether it's a network partition or actual node failure, so it doesn't do anything. And when you deploy a scale application out on Kubernetes, the application in like 10 minutes or something like that will go, I've gotten tired waiting for they have long timeouts because they're running on commodity hardware. It'll say, that replica's gone, I'm gonna rebuild the replica. If it came back, it's gonna, too late for me. But if the hardware actually failed, we may know that because we have agents on the hardware and we could determine if it went into a mode and failed in ways that Kubernetes is not hardware aware. That was my comment of, think of Kubernetes as software orchestration and think of us as hardware orchestration. We can circumvent the rebuild when you drain a node now. We want to automate this with our node management because we are paying attention to the hardware physical status of the nodes and understand if that node is in the same domain as 16 other nodes and 15 nodes are up, that node is gone. So, and again, the DriveScale, disaggregated compute and storage, we just find another node, attach to the storage, plug it into the applications, and you don't do a rebuild. Okay? So, that's a good thing, right? Yeah, more useful information. The stuff that Kubernetes gives, the CSI is somewhat obscure and not useful. So we're annotating things with the podwatcher. We want to extend those capabilities. Nothing else is important. By the way, there is support in the CSI for block volumes given out like a raw device, but none of our applications use case that we're supporting need it. So we don't have it in our current version of CSI. It's not a big deal to add, but if somebody asks for it, we'll give it to them. I'm done. The slides will be online. I know I kind of went fast. pp@drivescale.com. I like wine. I still like wine, Rory. Okay. I want to thank you guys for staying here. Jesus Christ. I hope you weren't doing it because you're polite. This is the last session, last day. I hope you had a great conference. All right. Safe trip home, wherever you go. Boston still? Yeah, see? I just had to find my car in the parking garage. Later, guys.